So we've been talking about rate laws, and so we looked at the rate of reaction related to the concentration of a reactant. And so we looked at zero order and first order and second order reactions. The integrated rate law gives us the relationship between concentration of reactant and time since the reaction began. So this allows us to predict what the concentration of a reactant or a product will be at some point in the future. So that's very useful. And of course, the integrated rate law depends on the order of the reaction because it depends on the rate law. So we're going to look at this very simple decomposition reaction again, where we just have one reactant and it decomposes into some products. Don't care what they are. So first order tells us the rate is directly proportional to the concentration of that one reactant. We can also express the rate this way as being the change in A over the change in T. And that's what we learned at the very, very beginning. There's a negative sign here because A is decreasing, whereas the rate is positive. There is no constant here because this is going to give us the average rate over whatever time period we're looking at. So we can equate these two things. If this is equal to the rate and this is equal to the rate, then those two things must be equal. And we can say that the negative change in concentration of A over the change in time is equal to a constant times the concentration of A. This is what's called the differential rate law. If we integrate that differential rate law, we get what's known as the integrated rate law. Now, if you've had calculus and you like calculus, there's a little sidebar in the text that shows exactly how they integrated it. Awesome, read that, be happy with yourself. Some of you have not taken calculus. I took calculus before you were born. So, I remember that it exists, and, I believe when people say calculus will do this, but I don't remember how to do integration. So if you're with me in that boat, we can just say, yeah, that happened, and this is what we end up with. So this is the integrated rate law. Just believe us. So this is taking that integrated form and expressing it in the form of a line. Right? Hopefully we all remember that. Y equals mx plus b. Y is what's graphed on the y-axis. X is graphed on the x-axis. So here we're graphing the natural log of the concentration at some time. And on the x-axis, we're graphing time. Then the slope is negative k, and the intercept is the natural log of the concentration at time zero, when things started, the initial concentration. So a first order graph, natural log of A0 is our intercept. We're graphing natural log of concentration versus time. We can also rearrange that and say that the natural log of the concentration at this time divided by the initial concentration is equal to negative k times the time. So the slope is negative, but the rate constant is positive. Any questions about that? Okay, so let's do an example. Consider the equation for the decomposition of SO2Cl2. The concentration was monitored at a fixed temperature as a function of time during the decomposition reaction. The following data were tabulated. Show that the reaction is first order and determine the rate constant. So what we did before is we looked at the change in the concentrations to see how that changed the rate. Here we've got this going over the course of 700 seconds, and the rate is continuously changing. And so what we're going to do is we're going to make a graph and use the integrated rate law, and we can get the rate constant that way. So this data would need to be graphed. Oh, it's not 700 seconds. There's another column, 1,500 seconds. So we would take this concentration of our reactant and calculate the natural log of this. This is typically not done just on a piece of paper with your calculator. You'd want to use something like Microsoft Excel. Once you get this data into the spreadsheet, then all you have to do is make the equation once, and then you can copy it, and it'll do all those calculations for you. It's a beautiful thing. So we did that, because who has time for that in lecture, right? So here's our graph. Natural log of the concentration versus time. We get this nice straight line. It's a little too perfect, but it's made up data, right? So we see that the slope is negative, and the computer will give us the best fit line using linear regression. That's why we like to find linear relationships. So y equals negative 0.0000029, too many zeros, times t minus 2.30. Okay, so we've graphed it. The question was asking us to show that this is a first order reaction. Well, if it's a first order reaction, the data should follow along a straight line. Does it? Yes, yes it does. So it's first order because natural log of SO2Cl2 versus time is linear. The integrated rate law, Y is the natural log of the concentration of that reactant, is equal to negative KT plus the natural log of the initial concentration. The slope is equal to negative K, right? Slope equals negative K. So if we want to know what K, the rate constant, is, this was one that's so simple that it's sometimes difficult. What does K equal? Negative slope, right? So we've got the slope right there. So all we need to do is change the sign. The rate constant then is 0.000290. Now here's a question. What are the units? First order rate constants always have the same units. It should be s to the minus 1. And another clue for that is when you look at this equation, t is in seconds, and if k is in reciprocal seconds, those units cancel out because these natural log terms don't have units. And so we need all the units to just kind of go away. So that's the rate constant. Any questions? This is a more accurate way of getting a rate constant instead of just comparing a couple of rates at different times and calculating it that way. We did that on Tuesday and we saw that it varied a little bit. In this way, the linear regression process does all of the kind of averaging for you, and you can come up with one good number. So now we're going to use that graph and the line to predict what the concentration will be at 1900 seconds. It's off the graph, but this is a linear relationship, and we can expect that the linear relationship will continue. So we've got our equation here. This is the concentration, natural log of the concentration of this at whatever time we're interested in, which is 1900 seconds. This is the intercept, the natural log of that. It's already in there for us. So all we need to do is plug 1900 in. So we've got natural log of SO2Cl2 is equal to negative 0.000290. I'm going to put the unit in there, times the time, 1900 seconds, then I ran out of room, minus 2.30. So negative 0.000290 times 1900 minus 2.30. So the natural log is equal to negative 2.851. That one came out with, and those are all the digits my calculator shows me. That's kind of unusual. Usually it'll show you a big old mess. It's fine to write that down, but I would always just keep the value from the calculator, because now we have to do the inverse log, right? And so use the value in their calculator instead of any rounded value, because rounding with logarithms can give you error very quickly. So this is going to equal e to the negative 2.851. So on my calculator, what I'm going to do is I'm going to press the e to the little square button, and then I'm going to move the cursor up to the previous answer and press enter, and it'll pull that answer into my new calculation. Press enter again, and I get 0.057786505. That's all of it. Now that's a ridiculous number of significant figures. Sig figs, when we're dealing with logarithms, especially natural logarithms, things get all kind of wacky. So we're not going to be super picky about sig figs in this class. But my general rule of thumb is more digits is better than fewer digits. You can always chop off the extra ones, but if you have too few, you can't get them back unless you do the whole calculation over again. Nobody likes to do that. So I'm looking at this problem to think, well, how should I report that answer? And I'm seeing, this has 3 sig figs. This is, at least 2, a little bit questionable. So maybe I'll round this to 3 sig figs, because it seems reasonable, right? So I'll probably call this 0.0578. And what's the unit on that? Molarity, moles per liter. Because in these calculations, all of the concentrations are given in moles per liter. Any questions? So this is more useful than just the rate law, because if you are actually doing this experiment, you may want to be able to predict, well, how long is it going to take before I get most of my product, or how long is it going to take until something happens, right? And so the integrated rate law gives us the relationship between concentration and time. Here's another one. Cyclopropane rearranges to form propene in the gas phase. The reaction is first order in cyclopropane and has a measured rate constant of 3.36 times 10 to the minus 5 per second at 720 Kelvin. If the initial cyclopropane concentration is 0.0445 molar, what will the cyclopropane concentration be after 235 minutes? Okay, lots of words, lots of numbers in there. It's first order, right? So we can use the first order integrated rate law. So we just write that out, natural log. Now, you probably don't know what the formula for cyclopropane is. We could just call it A, right? Natural log of A at time t is equal to negative KT. Is it plus or minus? I think it's plus. The natural log of A at 0. So that's the equation we need, and then let's look at what are these things that were given to us. Well, they gave us the rate constant. K is 3.36 times 10 to the minus 5 per second. They gave us the temperature. Is there temperature anywhere in that rate law? No, there isn't. The rate constant does depend on the temperature. It'll change with the temperature, and we'll learn later in this chapter how it changes. You'll often see a temperature specified, because this rate constant is only valid at that particular temperature. We don't have temperature changing or anything, so that's just a bit of information that we can just kind of ignore. We don't need to use all the numbers that are given in the problem. Initial concentration is given. That's a 0.0445 moles per liter. And we've got a time, T equals 235.0 minutes. So we're trying to find the cyclopropane concentration, so that's this A of T, and we can plug these values in here. There's going to be a unit issue though. You see what it is? Minutes and seconds, right? We need the time to be in seconds so that the units cancel with the rate constant. Well, that's not too bad. So 60 seconds per 1 minute. So we can convert that. $14100. That's what I gave it in minutes. Or 1.41 times 10 to the 4th seconds. So now our units are going to be okay, so we can plug these values in. So the natural log of A at T is equal to negative 3.36 times 10 to the minus 5 reciprocal seconds times the time, 1.41 times 10 to the 4th seconds. Those units are going to cancel out. Plus the natural log of that initial concentration, 0.0445 molar. So I'm going to do the math on the right side there. I'm getting negative 3.5860 and a bunch of other stuff. Anybody else get that number? When we're doing calculations like this, they're kind of complicated. And especially if you're not familiar with putting a whole bunch of stuff into your calculator at once, it's very easy to make a mistake. Even once you get comfortable with it, you can you say, well, I pressed the 3 button, but I didn't press it hard enough. And so you might be missing one of these 3s, and then you get the wrong answer. So I recommend always running through the calculation twice on your calculator. Do the calculation like this, write the answer down, clear it, enter it in again. If you get the same value, it's probably correct. If you get a different one, try it a 3rd time and go for best 2 out of 3. It's rare to have the same random mistake twice. Another thing I like about this calculator is it has the display screen and you can scroll back up and see what you did. And so then if you realize, oh shoot, I left something out or I did divided instead of multiplied, you can just go back up there and fix it and do it again. So that's nice. So here, this is the natural log of the concentration. So to get the concentration, we need to do the inverse log. So the concentration is equal to e to the minus 3.586. Or 0.0277. Is that a reasonable concentration? The one thing we know is that it has to be less than this, right? The reactant concentration will go down with time. So if it went up, check your math. Any questions? So second order integrated rate law. Looking at that same simple decomposition reaction. Here is the second order rate law. The rate is proportional to the concentration squared. We can also say that the rate is equal to negative change in A over change in T. This is true regardless of what type of a order the reaction has. It's the change in A over the change in T. So again, both of these are equal to the rate, so we can set them equal to each other. That's a differential rate law. It's negative dA over dt equals Ka squared. So we can integrate that. And again, we'll just say poof, it's integrated, and this is what we get. So here we have 1 over A at time t is equal to Kt plus 1 over A at time 0. We can graph that. That's also in the form of a line, y equals mx plus b. Our x-axis is 1 over at. The intercept is 1 over a0. Our slope is k. Here we see the slope is going to be positive, and that's just a factor of how the graph is, because the natural logs is what made things negative. So consider the equation for the decomposition of NO2. Concentration is monitored at a fixed temperature as a function of time during the decomposition, and the data is tabulated. Show by graphical analysis that the reaction is not first order and that it is second order. Determine the rate constant for the reaction. So what we're going to do is we're going to graph that data. We have to manipulate the data first. This is the concentration at NO2. That is what's measured. We need the reciprocal of that for our graph. So the reciprocal, we also need the natural log because I forgot about this one. So for first order, we have to graph the natural log of the concentration versus time. And so that's done here. And if you're not really paying attention, you might say, well, yeah, that's linear. No, it isn't. It's above the line here and at the end, and it's dipping below the line in the middle. These points are not evenly scattered on each side of the line. There's a definite trend. This thing is sagging in the middle. That's not linear. It's giving us a curve. It's not real pronounced, but it's a curve. So it's not first order because that's not linear. So if we graph 1 over the concentration versus time, now we get this, and that's a beautiful straight line. Real data does not always look that nice, but this is a definite trend that's away from being linear. So the computer gives us the best equation for the line, and there's our rate constant right there, 0.255. So the rate constant is the slope of this line. So there's not really any place down there, so I'll write it up. Well, yeah. Kind of have to choose a pen first before it'll let you write. K equals 0.255. Now, what are the units on that?
Wasn't it K equals negative slope?
That was the first order. Yeah, so first order, absolutely. The second order one, though, is positive. We can figure out what the units are by looking at the equation. It was 1 over AT is equal to KT plus 1 over A0. Oops. Obviously, seconds need to be in there somewhere, right? It's the rate constant times time. We need that unit of seconds to go away. So we're going to have reciprocal seconds in here somewhere. What's the unit on this term over here? 1 over molarity. So this term needs to collectively have 1 over molarity as its unit. So the rate constant, if we have reciprocal seconds, that'll cancel out here, but then we also need reciprocal molarity. We figured out those units previously in a different way. Any questions? So remember 0.255. Oh, I don't have to remember, it's there. Okay. Use the graph and best fitting line to predict the concentration of NO2 at 2,000 seconds. So we want to find the concentration of NO2 at 2,000 seconds. So T equals 2,000 seconds. And we've got this equation, right? Y in the equation is 1 over NO2. And say we forgot that. What's the axis label here? 1 over NO2. That's what Y is. At whatever time we're interested in, equals KT, so 0.255. And that was reciprocal molarity, reciprocal seconds, times the time, 2,000 seconds, plus 100. Well, 100 is the initial concentration, but 1 over the initial concentration. So that also has units of m to the minus 1. With these sorts of calculations, you don't always have to put the molarity units in there. The one thing that's important is if the rate constant has seconds in it, which it usually does, then the time has to be in seconds. You can't use minutes. Okay, so 1 over the concentration will be 0.255 times 2,000 plus 100. So 1 over the concentration equals 610. So how do I find out what the concentration is? I do the reciprocal of both sides. I upside down both sides. So the concentration of NO2 then is 1 over 610. There's different ways you can do that on your calculator. .01639,344. Probably 3 significant figures is good here. Molarity, moles per liter. Any questions? I'm just using the equation of a line. Zero order. So following that same process here, here's the rate law. The rate law has a to the 0 power, which is 1. So the rate is equal to the rate constant. The rate equals the change in a over the change in t. And so we come up with this. We integrate that, and we get this nice relationship, where the concentration of A is equal to negative KT plus the concentration initially. We plot concentration versus time. We don't have to manipulate the data. We get a linear plot, and the slope is equal to negative K. So K equals negative slope. And we're not doing a problem with that one because that one's like simple from the other piece, right? So now we're going to talk about half-life. You've probably heard about half-life before. We usually talk about this when we're dealing with like radioactive stuff and what's the half-life of thorium, whatever. So refresher, the half-life T1/2 is the time needed for the concentration of a reactant to fall to 1/2 of its initial value. And so if we've got an initial concentration of 0.5 and a T1/2 of 50 seconds, what would the concentration be at 50 seconds? Well, 50 seconds is the half-life. At 1 half-life, you cut the initial concentration in half. So 0.50 molar, 1 half-life, we're going to just divide by 2. So the concentration is going to be 0.25 molar at 50 seconds. At 100 seconds, that's 2 half-lives. It gets cut in half twice, right? So I'll take this one that's been cut in half, and I'll cut it in half again, and I'll get 0.125 molar at 100 seconds. 2 half-lives does not mean that the concentration has gone to 0. The half-life expression, how the half-life depends on the rate constant and the initial concentration, is different for different reaction orders. So we'll take the first order reaction first again. So the integrated rate law is given here. This is not the linear form of it, but it is the linear form rearranged. So this was on the first slide, we just didn't pay much attention to it. So the natural log of the concentration at whatever time we're at now divided by the concentration that it started with is equal to negative kT. When T is equal to the half-life, we know that the concentration at that time will be 1/2 of the initial concentration. So what we can do is we can plug 1/2 A0 in for a T. The natural log, well, I shouldn't use that. 1/2 A0 divided by A0 is equal to negative kT. T1/2. Because that's the definition of the half-life. It's when the concentration is half of what it initially was. Well, we can simplify this term, right? So there's fractions, right? That's A0 over 2 times 1 over A0. Another way to express that. The A0s cancel out. That is equal to 1/2. So the natural log of 1/2 is equal to negative kT 1/2. Well, we can calculate that. The natural log of 1/2 is negative 0.693. So this is equal to negative 0.693. There are other digits, but the next one is a 1, and so we usually just ignore the rest of them. Well, we've got 2 negative signs there, so we could just multiply everything by -1 and make these positive. Of course, that would make this one negative. And there we have k T1/2 is equal to positive 0.693. So to get T1/2 by itself, we just divide by k. And that's the half-life expression for a first-order reaction. The half-life does not depend on the initial concentration. Doesn't matter. Any questions? You do not need to know how to derive that, but if you can derive it, then you can figure it out when you've forgotten what the expression was. So it's a helpful thing. Yeah.
Sorry, I didn't follow where you got that 0.693.
Okay, 0.693 is the natural log of 1/2.
Okay.
So it's this, yeah. The natural log of 1/2 is negative 0.693, and then I made it, I multiplied by -1. Yeah. Any other questions? So the half-life is independent of the initial concentration. This is the sort of reaction that happens with nuclear decay. It's a first-order reaction. The half-life doesn't depend on how much stuff there was initially. So what we see here, graphing concentration versus time. If the half-life is 100 seconds, then after one half-life, you've got half as much as you started with. After 2 half-lives, it's cut in half again. After 3 half-lives, it's cut in half again. It's not a linear relationship. So a first-order reaction has, wow, the typos, has a half-life of 26.4 seconds. How long does it take for the concentration of the reactant in the reaction to fall to 1/8 of its initial value? We could do this problem 2 different ways. We can do it what feels like sort of a kindergarten way, or we can do it using math. So I'm going to do it both ways. We'll do the kindergarten method first. So we want to know how long for it to get to 1/8. So how many half-lives is that? So after 26.4 seconds, we've got 1/2 the original, and then another 26.4 seconds. This will get divided in half again. Now we'll have 1/4 after another 26.4 seconds. The 1/4 gets divided in half, and we get 1/8. We could do it just thinking about it like this, because we're looking at 1/8, which is a nice multiple of 1/2. So it's 26.4 times 3. 3 half-lives, 79.2 seconds. You can't always do it that way. So it's a first-order reaction. We know that T1/2 is equal to 0.693 over K. We don't know what K is, but we know what the half-life is. Can we calculate what K is? Yeah, we can. K is going to be equal 0.693 divided by the half-life. 0.693 divided by 26.4 seconds. .02625. Well, that doesn't answer the question. But we could use that in the integrated rate law and find out how long it took. So we had natural log of AT over A0 was equal to negative KT. The final concentration is 1/8 of the initial concentration. So AT equals 1/8 of A0. They didn't tell us what it was, but we can use a variable in there. So when we take this term in here, A at time t divided by A0 So that is a of time t is equal to 1/8 of a0, right? a0 over 8 is 1/8 of a0. And then it's also divided by a0. So this here came from this description up here. The concentration needs to be 1/8 of the initial concentration. AT equals 1/8 of the initial concentration. I have the 0 in the wrong place. This is a form of the integrated rate law. AT is A0 over 8. And then I'm dividing by A0. And so when I combine this, the A0s cancel out, and this is equal to 1/8. So the natural log of 1/8 is equal to negative KT. So if I want t, the time for this to happen, I want to divide by negative k. So, because, with negative sign, I don't want that with the time. Well, we know what k is. We figured it out already, right? It's this number up here. So I'm just going to write it in here. Oops. Negative 0.02625 reciprocal seconds. So t is the natural log of 1/8 divided by negative 0.02625. Any questions? That's algebra in there. I completely get that some of you are not good friends with algebra, but ask me lots and lots of questions. When you see me do something, like somebody asked me about the previous slide, how did you get that? That's an excellent question because probably several other people are wondering, what did you do there? Ask me, I'm happy to tell you. I'll explain a little bit in lecture, and if it's still not clear, meet with me during lab or office hours, and I will explain it as long as you're willing to listen, until it clicks for you, okay? Okay, what about the second order? So second order rate law, integrated rate law is this. Again, we can figure out the relationship for the half-life because we know that when t is equal to the half-life, we know that the concentration of A is equal to 1/2 the concentration initially. So we're going to plug in 1/2 of A0 for AT. We're taking this and we're plugging it in there. We have 1 over 1/2 A0 is equal to KT plus 1 over A0. So 1 over 2 is the same as 2. So I'm going to take that upside down fraction and straighten it out. So that's going to come up there. I just simplified that term. Now what we want to do is we want to separate t from everybody else. Here we've got multiplication and addition, and so we need to straighten those out first. We can combine like terms. We have 1 over A0, and here we have 2 over A0. So I'm going to subtract 1 over A0 from both sides. So that gives me 2 over a0 minus 1 over a0. Is equal to kt. Well, what's 2 minus 1? It's 1. What's 2x minus 1x? 1x. So 2 over a minus 1 over a is 1 over a. We get 1 over a0 is equal to kt. I want t by itself, so I'm going to divide both sides by k. And then I'm going to reverse it so that t is on the left instead of the right. T is equal to 1 over k times a0. That's the half-life expression for a second-order reaction. Yes? Okay. Which part? When I got this?
Yeah.
Okay, so let's,
Maybe it's probably
Okay, on the previous one?
on the first order example.
on the first order? Okay, so are you good on this one?
No,
You're not? Okay, so we'll work on that one. So we had 1 over AT, and we know that, pointer, okay, this, there, AT is equal to 1/2 of A0, right? So I'm going to plug that in for 1 over AT. So 1 over AT is 1 over 1/2 of A0. You okay with that? Well, I don't like these compound fractions, fractions within a fraction, right? So maybe we can separate this. 1 over 1 over 2 times 1 over A0. You okay with that?
I can't see it.
It's not writing. Of course it isn't. There it is. So, you okay with that?
Yeah.
Okay. So what's 1 divided by 1/2? It's 2. And if you don't like the algebra, flipping and stuff, do it on your calculator. 1 divided by 1/2. It's 2. So this is equal to 2. So that means I have 2 times 1 over AT. So that is 2 over AT. I'm sorry, not AT, A0. And so that's how I got this thing down here. Okay? Yes?
Why isn't K on the top of this part?
Why isn't K on top here?
Yeah.
Okay, excellent question. So I have KT, and what I did is I divided both sides by K. Oops, where did 5 come from? So the question is, wouldn't that put K on top? No, because it's not 1 over 1 over K. It's 1 over K. So maybe let's think about it in a different way. And let's clear that out there.
Is it because K is S, it's -1?
No. So let's do it this way. Instead of dividing by K, let's multiply by 1 over K. Okay? So times 1 over K. Those K's cancel out then, right? And so then this side is times 1 over K. now we see more clearly why K is in the denominator. Excellent question. These are those little algebra glitches that'll mess you up. Anybody else have any questions? I'll take that as a no. So, second order half-life. Half-life is 1 over the rate constant times the initial concentration. The half-life depends on the initial concentration. If you have a lower initial concentration, you will have a longer half-life. Zero order. So here's our zero order integrated rate law. And to find an expression for T1 half, we're going to do the same thing. The concentration at this time we're interested in is equal to 1/2 of the initial concentration. So I'm going to put 1/2 A0 in for AT. So 1/2 A0 is equal to negative KT plus A0. So I need to get all those A0 terms together. So I'm going to write this out as detailed as I can. Okay, so what I'm going to do is I'm going to subtract A0 from both sides. So I'm going to write this out as detailed as I can. I'm going to subtract A0 from both sides. I'm collecting like terms together. So on this side, A0 minus A0, that goes away, which is why I did it. So on this side, I have negative KT. Over here, I have 1/2 A0 minus A0. So that's going to be negative 1/2 A0. So that equals negative KT. I don't know about you, but I don't like the negative signs. We can multiply by -1 on both sides. Everybody okay with that? And that will get rid of the negative signs. So now I have 1/2 A0. Oops, I keep putting the 0 inside. It doesn't belong in there. 1/2 A0 is equal to KT. 1/2 A0 is equal to KT. So again, I want to move the K over. So instead of dividing, because it seems to make more sense, I'll multiply by 1 over K. So I've got K times 1 over K. That cancels out and leaves me just with T. Over here, I've got 1 over K, that's a times 1/2 times A0. So that's A0 divided by K2, or 2K, is equal to T, and that's our T1/2. Any questions? It's good practice to pull up the video, stop it when it's blank, and try to derive this yourself. It really helps you get comfortable with manipulating things and understanding what's going on if you work through it yourself. And then if you get stuck, press play. Excuse me, press play and see what I did. So there's the expression for zero order reaction half-life. For zero order reaction, the half-life also depends on the initial concentration, but here the half-life gets shorter when the initial concentration decreases. So that's the opposite effect from the second order. Okay, so this is a very nice table from your textbook that you will probably want to refer to a lot. Table 14.2, rate law summary table. It's got all of the equations that we've looked at. Okay, I might take this and post it as a page on our Canvas site just so you can pop it up there. I might do that just for my own reference. When you're doing these problems, try to come up with the equation that you need without looking at something like this. Try to remember what it is before you go looking for it. But then even if you feel very confident that, oh yeah, that's the right equation, just double check by looking at the table. Okay.